The focus of this video is understanding a type of graph called a histogram. In order to best follow along with this video, you'll want to have 2 sheets of graph paper or have a graph template on your tablet, a pencil or stylus respectively, and I recommend a calculator and ruler. Histograms are used to visually display quantitative data. This is rather important because if we have qualitative data, a histogram is not appropriate. For similar graphs with qualitative data, you would create what's called a bar graph. I'll return to that topic later. Histograms are used to group counts of raw data into intervals. This is the same function that we see in frequency distributions, but the histogram is in graph form rather than table form. Therefore, when you have quantitative data, you have the option of either creating a frequency distribution to group and show counts of data, or a histogram to group and show counts of data. It really depends on which one you prefer and the audience to whom you're going to share the information. If your audience is comfortable and used to seeing things in graph form, the histogram is a good option. Let's take a moment to look at a few histograms to get a sense of them and their layout. Take a look at these 3 graphs, pause the show, and pay attention to differences and similarities in them. Pay special attention to the x-axes, y-axes, and the shape and location of the bars. Let's start by looking at what we've noticed about the x-axis. The x-axis has values counting from lower to the left to higher at the right. This is true in all 3 of the graphs. One of the differences you might notice, however, is that one of the graphs, the gray one at the top, has movements that are single-digit movements, while the other graphs have movements that are in larger intervals. You might also notice that the anchor or label for each bar is located centered underneath each bar. Even in the case of the purple graph, where the anchors or labels of each bar are quite long, they're set at an angle that still aligns itself with the center of each bar. Now let's look at the y-axis. You should notice here that the y-axis in all 3 graphs is referring to count in some way. In the top graph, it refers to it as the number of cases. In the purple graph, it refers to it as the frequency or number. And the third graph again refers to it as the number of winners. So we know that the y-axis is telling us about frequency or count, and the x-axis is telling us about score movements that are quantitative in nature. Now let's take a look at the bars. One thing you might have noticed is that there's no gaps between any of the bars. The only time you see an empty space is actually when it's representing an absence of information. That is, when there's no data present in a score interval, such as in the bottom graph where we see nothing from 0 to 19. But in all of the other cases, our bars are touching each other anytime data are present. And this is true in all of the graphs. The lack of gaps is referring us to the fact that the x-axis is about something that's truly continuous or quantitative in nature. So to summarize, our x-axis represents continuous quantitative data, while our y-axis represents frequency with which those quantitative values occurred. In addition, adjacent bars touch to represent the continuous nature of quantitative variables. Let's move through the steps it takes to create a histogram, starting with step 1. We need to choose the appropriate interval for a quantitative data set. Remember, if your data are qualitative, you cannot use a histogram. If the range of your data is quite small, such as moving from 0 to 12, you can use 1-unit intervals. However, if you have a larger range to your data, such as 10,000, 100,000, 47, 125, you would need to use larger intervals to best summarize your data. For example, in some large ranges, we might want to use interval sizes of about 10,000 units. When constructing your intervals, you must be sure that the size of each interval is equal, that the intervals subsume all of the raw data, and the intervals must be intuitive. That means they must move in numbers that we're used to counting in, like moving in 1s, 2s, 5s, 10s, 20s, 50s, 100s, anything else that's easy for you to count in. In general, If the interval is easy to count in multiples of, like 10, 20, 30, 40, 50, then it's likely an intuitive one. But if it's one where it takes a little bit more processing in the brain, that is, you have a slower multiplication count when you're doing this cognitively, then it's probably not a good interval. 7s, 8s, 16s, 28s, those are not numbers we typically can easily do multiples of in our head, so they don't make for good intervals. Let's try it out. Assume that our variable is income in dollars, and the highest score we see in our dataset is $249,000, and the lowest score we see in the dataset is $12,000. Pause here and try to choose the appropriate size for your interval. We do want to have about 10 to 20 intervals typically in our histogram. If you have fewer than 10 intervals, you're probably creating intervals that are too large. If you have more than 20, you're probably not doing enough summarizing. So try to find a size for your intervals here that'll yield approximately 10 to 20 intervals, and we'll subsume scores going from 12,000 all the way up to 249,000. As a hint, start by finding the range, and then try to break that into intervals. The exclusive range, also often referred to simply as the range, is equal to the highest number in the dataset minus the lowest number in the dataset. So our range here is 237,000. Now try to break this down to get the approximate size that each interval should be if we want to have approximately 10 to 20 intervals. Remember, it's more important that your interval be intuitive than that you have exactly 10 to 20 of them. I can now get the approximate size of my intervals. If the range is 237,000 and I want to have about 10 intervals, that's going to mean that each interval is going to be about 23,700. This is not an intuitive number for us to count in multiples of, but it is pretty close to one that is easy, 25,000. So I could use 25,000 as the size for my interval. If I want to use 20 intervals, I would take my 237,000, divide by 20, and that would yield for me an interval size of about 11,850. Again, this one's not intuitive, but it's pretty close to another number which is an intuitive one for us to count in, and that's 10,000. Therefore, my best options are to use interval sizes of about $25,000 or $10,000. Either one is appropriate, but if we want more summary, we would use $25,000, or if we want more specificity, we would use $10,000. Take a moment here to test your understanding of the concept. I've listed 5 variables here: age in years, rainfall in inches, ounces of juice consumed, miles walked, and monthly dollars spent on media. I've also indicated the lowest score and the highest score in each of these theoretical raw data sets. For age, the lowest was 1 year, and the highest was 99. For rainfall in inches, the lowest was 0.00, and the highest was 2.75. For juice consumed, the lowest was 0, and the highest was 25. Miles walked, the lowest is 0.2, and the highest is 8.6. And monthly dollars spent on media, for the lowest we have 12, and the highest we have 206. Pause here and consider what the appropriate interval size might be for each of these 5 variables, so we yield that approximately 10 to 20 intervals. Keeping in mind, it's more important that our intervals be easy to move in, that is, that they be intuitive, than that we have exactly 10, 20, or somewhere in between. It's also fine to have 16 intervals, 9 intervals, 12 intervals. It doesn't have to be exactly 10 or exactly 20, but that gives us a nice range within which we want to have our intervals. Keep in mind that the number of intervals and the size of the intervals are different things. If you're ready, let's review. For age, the appropriate interval size is 5 or 10. For rainfall, the appropriate size would be 0.25 inches. If we use this interval size, we'll end up with 12 intervals. This is within our 10 to 20 range and is a good fit. It's also easy to count in 0.25, 0.25, 0.5, 0.75, 1, so it's meeting our criteria. For ounces of juice consumed, interval sizes of 2 are probably best. We could use 5s, but then we're going to only yield about 6 intervals. However, if we use an interval size of 2 units, and we start by counting 0 to 1, then 2 to 3, so on and so forth, we end up with 13 intervals. Comparatively, counting in fives only gives us those 6 intervals, and it's probably too much summary and not enough specificity. For miles walked, intervals of 0.50 would be optimal. That'll yield for us about 17 or 18 different intervals. And for monthly spending on media, intervals of 10 or 20 would be appropriate. If we use an interval size of 10, we'll end up with approximately 20 intervals. And if we use the interval size of 20, we'll end up with approximately 10 intervals. Let's try a practice on choosing the appropriate interval and identifying issues with intervals. Remember, we typically want about 10 to 20 intervals, though it doesn't have to be exactly 10 or 20, it doesn't have to be exactly between these numbers. 9 or 8 intervals can be okay, 22, 23 can be okay, as long as the other things are true, that the intervals are all equal in size, they subsume all of the raw data, and they're intuitive or easy to count in. For our practice, we'll be focusing particularly on the equal size of the intervals and the intuitive nature of the intervals. There's one last thing we'll need to consider when we look at the intervals, and that's whether they are mutually exclusive. Intervals are mutually exclusive when they don't overlap. If we have overlap in the intervals, then a raw score can appear in 2 intervals and be counted twice. This would yield for us the wrong sample size, also known as n. This can cause our graph to provide erroneous information or otherwise be misleading, and we want to avoid that. The goal of making any graph or table is to make your summaries easy to understand in an intuitive way. Clarity and accuracy are the hallmarks of a well-constructed table or graph. Let's take a quick look at an example here. Assume our interval sizes are 15 to 20, 20 to 25, 25 to 30, and 30 to 35. If I have a raw score of 17, it's easy to locate. It belongs in the row that corresponds to an interval of 15 to 20, so I could put a 1 in the frequency column there. But what if I had a score of 25? It's harder for me to deduce where that should go, because it could either go in the section that goes from 20 to 25 or from 25 to 30. If I put it in both of those locations, I'm going to end up with that number being counted twice. And this is going to give us the erroneous sample size here of 3 when we've actually only had 2 pieces of data entered. For this reason, our interval sizes must be mutually exclusive. Here's an option. I could create intervals going from 15 to 19, 20 to 24, 25 to 29, 30 to 34, 35 to 39. Now, we don't have the 10 to 20 that we want, but I'm using a shorter version here just for the example. Now, if in this case I had a score of 17, I could easily locate it in that 15 to 19 space. If I had a score of 25, I can easily locate that it goes between 25 and 29, or it corresponds with the row for the interval 20 to 29. Then I don't have that issue of double counting here, and I can easily see when I fill in my other zeros that my 2 data points are in the intervals of 15 to 19 and 25 to 29. Here you have 4 data sets, each represented by a different color. You'll notice that each of these sets of intervals does have close to 10 intervals. So as you're assessing these, focus on whether they are equally sized, that is, each interval is spanning the same number of units, and whether they're moving in intuitive quantities. You should have spotted some errors, so I'll start here by looking at the blue variable. You should have noticed that the intervals are not mutually exclusive because we have one interval ending in a 5 and the next one starting with 5. So if we had a raw score of 5, we don't know which interval it's supposed to go into. This is actually true of all the intervals. 10 appears twice, 15 appears twice, 20, 25, all the way up. So this one has already broken one of our rules. Let's take a look at the yellow one. We don't have that violation of the overlap of the intervals, so that's good. Now we need to check for our other 2 issues. Are the sizes equal and are they intuitive? Though it's hard to spot, these are not equally sized intervals. Take a look at our first interval. It goes from 10 to 20. Though that sounds like it's a 10-unit movement, it's actually an 11-unit movement. This is because it subsumes 11 different numbers: 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. That's a total of 11 different digits. In contrast, the interval that goes from 21 to 30 only subsumes 10 different digits, and this is true of all of the other intervals here. So the interval that's breaking the rule here is that first one going from 10 to 20. So the intervals for our yellow variables are also incorrectly constructed. Let's now turn our attention to the green variable. We see that our categories, our intervals here, are mutually exclusive. We've got ending in a 4, beginning in a 5, ending in a 9, beginning in 10, so everything's good there. We also have equally sized intervals. If we look at our first interval, it's moving from 0 to 4. That's 0, 1, 2, 3, and 4. That's a 5-unit movement. Our next section, 5 to 9, is also 5-unit movements. 5, 6, 7, 8, 9. That's 5 different digits. And if you count all the way up, that continues to happen. So 2 of our rules have been met adequately with the green variable. Now let's look at whether we're moving in intuitive intervals. Well, these are counting in 5-digit increments. 0 to 4 is 5 digits, 5 to 9 is 5 digits, so on and so forth. And the brain can easily count in 5s. This is clear to us if we look at the left side column of our intervals, 0, 5, 10, 15, 20, 25, 30, 35, 40. That's easy for our brain to follow. So the intervals are properly constructed here for our green variable. With all that in mind, take a look now at the purple variable list. A couple of things appear to be largely working here. Our interval sizes, if we look at our first 2 intervals, are the same. We've got a 5-unit movement and a 5-unit movement. We also see that these are mutually exclusive. We go from a 5 at the end of one to a 6 at the beginning of the next. But then if we look at our third interval here, we start to hit some issues. We've got 7 as the start and 15 at the end point. This is not equal in size to the previous interval, which was counting in only a 5-unit movement. In addition, starting with 7 causes an overlap with the end of the previous interval, which went up to 10. What could be done here to fix the purple intervals? Try to come up with the simplest solution possible. If you notice that changing the 7 to an 11 would fix our issues, you're correct. Now our intervals are the same size and mutually exclusive. They're also counting in units of 5, so they are intuitive. Now I'm going to take a moment to compare the green intervals to the purple intervals. Which one do you prefer? I often find that people prefer when the intervals are more like the green one. The difference between the two, other than how many intervals there are and where they end, is that the intuitive counting numbers appear on the left side of the intervals in the green variable, and they appear on the right side in the purple variable. These are both correct ways of presenting the data. We might prefer to use the green version if we have a 0 in our data set. We might prefer to use the purple one if the lowest number in our data set is a 1. Though each of these are appropriate, it's really up to the person making the graph which one they prefer. I typically see folks using the form that adheres to the green style, where we have the intuitive numbers counting at the beginning of each interval rather than at the end of each interval. With all this information in mind, take a look again at those histograms we had earlier in our video and see if you can find any errors on the X or Y axes. Take a look at the intervals in the purple graph. The first interval goes from 0 to 10, and the second goes from 11 to 20. These are not equally sized intervals, so we have an issue here in the purple histogram. Now take a look at the orange histogram. We have another issue happening. The first interval goes from 0 to 19. That's a 20-unit movement, but the second one goes from 20 to 29. Again, we have an issue here. So pause and think about what we could do to fix the issues in each of these. If the data allow, for the purple graph, we could change our first interval to start at 1 and end at 10. Of course, if we had any zeros in that data set, we would need to change this and go from 0 to 9, 10 to 19, so on and so forth. In the orange graph, we would need to add an interval and split that interval of 0 to 19 into 2. However, only people aged 18 and older are typically allowed to play in the lottery, so let's assume that's true of the area in which these data were collected as well. In that case, our first interval doesn't need to go from 0 to 9, so we can just add one empty interval going from 10 to 19. How about the gray graph? The x-axis looks pretty good, but let's take a look at our y-axis. We have some pretty big movements here, and it makes it a little bit difficult to know exactly where each of the bar heights aligns. Take a look at our first bar. It's hard to know exactly where it's lining up, but we know it's a little bit less than 10,000. So what could be done to improve the ease with which your reader can understand the approximate height of your bars? If we break the frequencies down so that we're showing marks at 1,000, 2,000, 3,000, 4,000, 5,000, that is, if we move in 1,000 unit increments instead of 5,000 unit increments, that'll make it easier for us to get a good approximation of the height of each bar. One last thing to note is that we've got some empty space at the top of our graph. This is appropriate. It helps us to see where the bars end. If we cut the graph off so it's flush with the highest bar, we wouldn't actually know that we'd hit the top of that bar. We wouldn't know if the frequency was actually higher than the graph was showing. So for that reason, we typically will leave some gap on the top of the tallest bar and keep that consistent across the whole graph, use the same height for all, and you'll sometimes even see some space left at the left or right side of the graph, though you don't see that indicated in any of these three examples. We're now ready to build a histogram and move through all the required steps. Let's review the steps. The first step was to choose an appropriate interval. Because that's a little bit complicated, we've spent a good amount of time practicing that. We're now ready to move on to steps 2 and 3. In step 2, we will create our template by filling in the x-axis and the y-axis. We'll use the interval sizes to fill in the x-axis. In step 3, we'll create bars over each interval to represent the raw data counts. And then when we're done with all of that, we'll polish our work by adding an appropriate and simple title at the top. Let's get started by looking at some raw data. These are fake data made for our purposes. Assume the data presented on this slide are income represented in dollars for employees that are all at the same company. Notice how overwhelming this data set is. Even though the data are listed in order from lowest earner to highest earner, it's still a lot of information for us to try to make sense of. Pause here and look for patterns and try to think about how you would summarize the income listed in this data set. The first thing you might look at is the lowest number relative to the highest number so that you can establish the range. We get 125,000 minus 11,500, which gives us a range of 113,500. If we wanted to use that to try to create approximate intervals, we could divide this by 10 or 20. I'll start with 10. When we divide by 10, we get an approximate interval size of 11,350. That's pretty close to 10,000, which would be an easier or more intuitive number to count in. If I divide by 20, I get 5,675. This one's pretty close to the interval of 5,000. So my two options are to use $10,000 intervals or $5,000 intervals. Let's go with the 10,000. Next, we need to find the appropriate height for our y-axis. We need the y-axis to be slightly taller than the tallest bar will be. So we need to figure out which interval is going to have the highest frequency within it, and then make sure our y-axis goes at least 1 unit beyond that. We chose an interval size of 10,000, so let's presume our intervals will go from 0 to 9,999, 10,000 to 19,999, and so on. There are no data that would appear in the first interval going from 0 to 9,999, so I'll focus on the data that fall in the $10,000, $20,000, $30,000, $40,000, and so on ranges. We see about 4 numbers here that fall in that first range from 10,000 to 19,999. There are 6 numbers that are falling in the $20,000 range. We have 8 numbers falling in the $30,000 range. If we look at the $40,000 range, we again see 8 numbers. The $50,000 range is a bit larger here. I see 14 numbers that appear. There are 11 numbers in the $60,000 range, 8 in the $70,000 range, 5 in the $80,000 range, 3 in the $90,000 range, none in the $100,000 range, but we do have 1 in the $120,000 range. The interval with the largest frequency has a frequency of 14 raw scores. So we'll need our y-axis to be at least 15 units tall so that all of our bars will fit and there'll be a little space at the top. It's also a good idea to take note of the sample size. We have 68 pieces of raw data here. We can use that to make sure that the frequency or the height of all of our bars in our histogram are equal to 68. Otherwise, we know we've either added erroneously a piece of data or we missed a piece of data. We'll now draw our 2 lines to represent the x-axis on the bottom and y-axis along the side, which meet at a 90-degree angle. For my y-axis, I've chosen to go all the way up to 18. Our tallest bar will be 14, and that'll leave a nice amount of space visually at the top of our graph. We can now fill in our x-axis. You can choose to start your x-axis at 0 or even 10,000, but I decided to leave a little bit of space and start the first notch on the x-axis at 0, and then I moved up in $5,000 increments so that my bars will be 2 increments thick and make them a little bit easier to read. It'll make the graph more appealing. Our first interval with data went from 10,000 to 19,999, and we had 4 pieces of raw data in that span. So our first bar is going to go from 10,000 to about 19,999 and reach up to a height on the y-axis of 4. Using the same logic, we can fill in all the other bars along the x-axis. To make my graph a little cleaner and more appealing, I've redrawn that first bar using my ruler and then filled in all the other bars using that ruler. Take a look and you might notice that the center of each bar is marked by the center of the interval. For instance, the first bar that went from 10,000 to just under 20,000 has a midpoint marker of 15,000. I can clearly see my tallest bar hits the y-axis at 14. I can also look at the lineup of all of my other bars. I have one that's hitting at around 11. I've got several that are hitting around 8. I've got one hitting at a count or frequency of 6. One hitting at a count or frequency of 5. One hitting at a count or frequency of 4. One at a count or frequency of 3. And just one hitting a frequency of 1. You might also have noticed the sloping bell-shaped nature of our curve. That means that the values that are most common are the ones in the middle ranges, like in the $50,000 and $60,000 ranges. And then when we get to the relatively low earning levels and relatively high earning levels, the scores are uncommon because the bars are getting shorter at the ends relative to when we're in the center of the curve. We can check n by identifying and adding the heights of all of the bars. When we add all the heights together, we do yield that sample size of 68 that we noted earlier. So things are checking out so far. It looks like we didn't omit any of the data and we didn't erroneously add any data into the data set. You might recall that some of the graphs we saw earlier gave the interval range underneath the bars instead of the midpoint underneath the bars. We can easily make a change to our graph to do the same. I can remove the data points under the first intervals, and I can replace it with the range, which was 10,000 to 19,999. In so doing, I get the interval ranges appearing at the bottom of each of the bars rather than the endpoints and midpoints for the bars. These options are equally acceptable for our goals today. Here we have an example of a histogram on the left and a bar graph on the right so that we can make some comparisons. You'll notice in the histogram, as we noted before, the adjacent bars are all touching. When you see an empty space or a gap, that means that there were no scores in that interval range. But when we look at the bar graph, we see gaps next to adjacent bars. And though there's a similarity here in the y-axes because they each represent frequency, there's a clear difference when we look at the x-axes. The x-axis on the histogram is moving quantitatively. That means we're seeing numbers for the intervals. But the x-axis of our bar graph is different. We're seeing names down here. The names are groups A, B, C, D, E, and F. When we see words, names, or letters on the x-axis, that's an indicator to us that we're looking at a bar graph, and these are qualitatively different groups, where we're seeing quantitative change along the x-axis of a histogram. That's it for our tutorial on histograms. If you're not ready to move on, you can do this bonus practice of finding the errors in the graph below. Pause and hit play again when you're ready to check your work. There's a lot of things you could have noticed here. First, our intervals are overlapping. So we don't know where a 20 would go or a 40 would go. They could go into two different bars at the same time, but there's a bigger issue here. We have gaps between the bars, indicating that this is a bar graph and not a histogram. However, if we look at the x-axis, we have quantitative movements. So we can't tell if this is supposed to be a histogram or a bar graph. Because the data on the x-axis are clearly quantitative, this should have been a histogram with bars touching. You might have also noted that it would have been helpful to have more anchors on the y-axis or labels, because it is a bit hard to line the bars up with their location on the y-axis. That's it for this segment on histograms. Keep the skills we discussed here in mind when working through homework and when looking at graphs that you find at other locations such as online.